Physics is unforgiving. When designing complex systems, textbook tolerances often fall short, and the cost of design debt eventually must be paid. This video explores the anatomy of a thermal catastrophe and how predictive monitoring can prevent total system failure. Consider the ethylene oxide Plug Flow Reactor. While ideal models assume perfect radial mixing, the physical reality involves boundary layer stagnation and catalyst dust, leading to thermal dead zones. AI intelligence modules now map these thousands of tubes to flag safety limit breaches instantly. Think of molecular reactions as a traffic jam at a toll booth. On a microscale, catalyst pores create similar congestion. Diffusion limits mean the interior reacts slower than the surface, causing heat buildup. Machine learning models now forecast this decay to adjust temperatures dynamically. Industry has evolved from batch pots to continuous flow. We have moved from simple time-dependent processes to complex space-dependent systems. AI models now calculate the precise geometric scaling factors needed to prevent fluid channeling during full-scale deployment. Relying solely on 2D logic is a trap. In reality, parameters are distributed, not lumped. AI agents can audit PNIDs to identify logical control loops or missing relief valves before physical components are even manufactured. When we analyze fluid and steel, we must account for microscopic mechanical mazes rather than uniform vectors. Computer vision AI can analyze X-ray CT scans to map real-world catalyst loading, feeding these imperfections back into our digital models. Mathematics can be brittle. Phenomena like the Leidenfrost effect can invalidate linear assumptions instantly. Physics-informed neural networks, or PINs, help solve these complex, nonlinear equations significantly faster, enabling real-time safety calculations. We can bridge the gap between ideal simulations and reality using surrogate physics. By predicting hotspot formation milliseconds before it occurs, models allow for preemptive action, continuously validating against physical sensor data. A digital twin acts as a nervous system for industrial steel. By allowing the system to feel through data, we can detect anomalies and mute faulty sensors that might otherwise trick the model into identifying phantom issues. Traditional PID controllers often struggle with actuator lag and overcorrections. Reinforcement learning offers a predictive approach, utilizing state-based anticipation to execute graceful shutdowns while keeping the system within safe temperature limits. Shop floor reality often contradicts digital models. Uneven catalyst loading causes severe flow channeling. Using edge AI to verify packing density through acoustic monitoring ensures that potential voids are caught before operations begin. Fouling is rarely uniform. Patchy, asymmetric accumulation creates localized thermal stress that can bend tubes. Time series decay forecasting tracks these minute shifts over months to optimize maintenance schedules before a safety trip is required. Generative design allows us to evolve complex geometries, but we must account for manufacturing constraints. AI loss functions ensure these organic lattices are printable, avoiding uncleanable dead zones where side reactions could occur. On a planetary scale, we are bound by thermodynamic limits. However, top-level AI architectures can orchestrate feedstock routing across global networks of microreactors, minimizing entropy and maximizing overall yield. We cannot defeat entropy, but we can manage it. Through AI-driven physics, we can increase conversion efficiency and eliminate catastrophic downtime. It is time to apply these tools to the shop floor and build it right.